Right. Okay, I'm going to very briefly review stuff that we've learned and then move on again. There is a homework assignment that's due tonight. The reason I have a homework assignment due tonight is because I'm going to be lecturing on new stuff today. I can postpone it if that is what you want and just have it due on Wednesday after the test. But there will also be an assignment based on today's material. So tell me what to do.
It doesn't hurt, just put it off.
Postpone.
Because learning today and Wednesday doesn't
Okay, Court.
Yeah, you want to do Wednesday? Yeah, move it.
Anybody opposed to that? I mean, you can always do it earlier. I just want to make sure. Yeah. Okay, so I will do that. I will move it from due today into due on Wednesday. Okay, so what's going to be on the exam? Obviously, it's the material that we've covered this semester so far. To make sure it's clear, the exams are cumulative only over the given semester. So like the final this semester is only cumulative over second semester, but you can't solve hardly any of the problems from second semester without a pretty good knowledge of first semester material. So there won't be questions that are, simply questions of mechanics or dynamics, but there will be questions that involve mechanics dynamics in an electrical and magnetic problem. So you still have to be able to do that stuff. So let's look at what we've covered. So chapter 18. In chapter 18, we learned about electric charge and the electric field. Electric charge, you have the two types, positive charge and negative charge. It comes in discrete amounts, positive or negative, the charge of an electron. We saw that when you rub materials, you separate charge. You can't create or destroy it. You simply separate it. And we had the basic rules that opposites attract, likes repel. So positive attracts negative, positive repels positive, negative repels negative. Coulomb's law, our equation for the force between charges. So there's the first equation of this. Looks just like Newton's universal law of gravitation, except for you replace the gravitational charge, i.e. the mass, with the electric charge, which we simply call the electric charge. So it's still an inverse square law. So you double the distance, you have 4 times the force, well, 1/4 the force, excuse me. One difference between Coulomb's law and gravitational is because you have 2 types of electric charge, you have 2 types of interaction, attractive or repulsive. Whereas with gravity, you only had 1 type of interaction, attractive. Then we talked about electric field. An electric field is completely analogous to gravitational field. It's a force field. It's a field we use to find force. So the purpose of electric fields is so you can find the force more easily from a collection of charges. And so what do we do with electric fields? Well, we take advantage of the equation. Force is equal to QE to find the force because that's really its purpose. And then we do lots of not as fun things like find the electric field due to these 3 point charges. And so when you're finding the electric field due to point charges, you add the electric fields as vectors. You just find what each individual electric field is and add them together as vectors. So remember, the electric fields have rules of going out of positive and going into negative. So if you have a positive charge, you know the electric field's pointing out. Negative charge, you know it's going in. The electric field direction is indicated by direction of the arrow, and that's the direction the force will be on a positive charge. Why on a positive charge? Because if Q is a positive number, then the F in this equation is the same direction as the E. If Q is a negative number, it's going to flip the directions. We had the equation, Coulomb's law was force is equal to K Q1, Q2 over R squared, where R was the separation of the centers. So for a point charge, the electric field has a magnitude of force electric over Q2. So for a point charge, the electric field is going to be magnitude of K Q1 over R squared. So I find magnitudes separately from directions and then add as vectors. Gauss's law is something that this year we only covered in Physics 252. So people in Physics 152 will not have to know Gauss's law. That's going to be 252 only. Insulator, yes.
It's a marking on the one
I'm writing it in OneNote, so it is at some level. It may not have updated yet, and I'm sorry about that, but it is at some level recording it. Okay, conductors and insulators. The fundamental difference between a conductor and an insulator is not which one can have charge. Oftentimes we think only a conductor can have charge. No, both of them can have charge. But in a conductor, charge is free to move about, almost free to move about. And so the charge will distribute it everywhere in the conductor. And then we learned specific rules that were based on Gauss's law that said that the charge on the surface of is all on the surface of the conductor. There's no charge in the middle of a conductor. And the electric field inside of the conductor is zero. So the conductors, because the charge can flow, we gave arguments why the electric field has to be zero, because if it wasn't, there'd be a net force on charge inside the conductor that would make it move until you got to the point where the electric field was zero. Likewise, the charge then on the surface is going to make electric field lines that are always normal to the surface, because if the electric field at the surface wasn't normal, there would be an electric field component parallel to the surface, and charges would have a force moving them on the surface, once again causing it to redistribute until you reach equilibrium when there's no horizontal forces on the surface. Insulators, charge can't move. You can add charge to it, you can take away charge from it, but you can't make charge move from here to here. So the insulator is just, the charge takes a lot of energy to move it. Then in chapter 19, we talked about electric potential. What's the common term we use for electric potential? Voltage. Despite what the textbook says, there is no difference in voltage and electric potential. Electric potential / voltage is defined as the change in potential energy per unit charge. Because potential energy is defined as a change, both electric potential and voltage are defined as a change. Right? The book tries to make a distinction there, and there is none. So the electric potential energy per unit charge is the next thing we have to be able to calculate. Well, Coulomb's law gives us that the electric potential energy is K Q1 Q2 over R. How is that different from Coulomb's law telling us the force? Okay, instead of being over R squared, it's over R. And something that you wouldn't see in the equations I wrote, Coulomb's law, the force, is a vector equation. I always just use the rules that opposites attract and likes repel and don't write that vector equation. But potential energy is a scalar, so this is a scalar equation. There is no directionality to potential energy. And since that's potential energy between 2 point charges, then I can find the voltage due to 1 point charge so the voltage due to a point charge is KQ over R. Now, once again, that's for a point charge. If you have more than one charge, it becomes more complicated. And so we learned about capacitors, things that, what does a capacitor store? This is an important thing to me. It stores energy in the form of an electric field or in the form of a separation of charge. Ashley is ready. At least for that question she is. So a capacitor stores energy in either the form of an electric field or in a charge separation. And so with those capacitors, we learned that they make electric fields that are uniform, and the relationship between electric field and electric potential for a capacitor is delta V is equal to E D, where D is the distance you've gone parallel to the electric field. It has to be parallel. If it's not parallel, then that ain't going to be right. So I'm going to change this to having vectors and a dot product, because dot product means multiply the parallel parts. So the voltage difference is electric field dotted to the distance that you traveled parallel. Note that there is no voltage change if you move perpendicular to the electric field. And that makes perfect sense because there is no change in potential energy if you move in a direction that has no force. And so you move perpendicular to the electric field, you're moving perpendicular to the force, no work done, no change in potential energy, no change in electric potential. So capacitor, we have that equation, delta V is equal, it stands out a lot better, by the way, on my screen than it does up there. I thought this color was going to look great for you guys. I look at the screen now and I realize not so much. Sorry about that. Whoops. That was not the right button to press. What I did there apparently was make a new page. What I was going to do is just select everything and change the color. What's a good color? Does the blue show up well? Black?
Yellow.
Okay, hey, yellow. I'm kind of curious what will happen if I hit the highlighter, but I'm sure it won't be good. Does that stand out okay? Darn it. This is a fine way to use my time.
It doesn't work as bad on the computer.
Well, yes, on the computer, I know, but you're looking at it primarily. I'm doing really well with this. I'm sorry. Okay, let's go with Corso suggestion of black. I was wrong. Okay, he says well, white isn't going to work because I have some of it on white. Okay. I will. Yeah, sure. Okay, yeah, I know. You've taken half the class just trying to choose a color. So, yes, well, yellow. There's yellow. Okay, we're going with that, and we're moving on. Okay, so that kind of works as long as I don't go on to the white. Okay, other things we learned for capacitors was Q equals VC. The equation that actually identifies capacitance. Capacitance is defined as the voltage difference between the plates divided by the charge separation divided by the voltage difference. So that's the defining property for capacitors. And the energy stored in a capacitor, that U means potential energy. It's hard because in one class we use one symbol for potential energy, another we use another. Believe it or not, V is also a symbol used for potential energy. That's what we're using in my quantum class. So it gets a little confusing looking at the symbols. But the potential energy stored by a capacitor is 1/2 CV squared. And remember, we were actually able to take that and calculate the energy density contained in an electric field, which is going to turn out to be really important after we get past the next test. Chapter 20 was all about Ohm's law and being able to do circuits, 20 and 21 circuits. So make sure you have a reasonable understanding of the safety with electricity, what makes, what you can feel, what will cause your heart to go into fibrillations, what causes your muscles to contract and you not to have control. One thing that I have not been careful about is the equation for power. Power in an electric circuit is current times voltage. And it's actually really easy to wave your hands at why that's the case. The voltage change is the potential energy per unit charge. And the current is the charge per second that's passing. So if each charge has a voltage change V, then I just take the amount of charge per second that passes times the voltage change for each charge gives me the energy per charge times charge per second, the energy per second that is being taken away by something or provided if it's a power supply. So power is always IV, always. Only for a resistor, then we can replace V equals IR to also get power is equal to V squared over R is equal to I squared R. So the bottom set of equations only works for a resistor. I myself have taken the bottom equations and tried to apply it to a power supply. Well, power supply, an ideal power supply has no resistance. How do you do that with no resistance? You cannot. It requires a resistor to use one of the bottom two equations there. Make sure you understand how the electrocardiogram is working. That is, what are you measuring when you use an electrocardiogram? You're measuring voltage differences from the surface of the body. But those voltage differences are telling you about what's going on, the voltages and the currents in the heart. And so those voltages on the surface are telling you about what's going on in the heart. And so by looking at how those voltage differences change, we can then get information about what's going on in the heart. And of course, I didn't talk about the electroencephalogram, but the electroencephalogram is putting probes on your head and measuring voltage changes on the skin of your head. And by measuring the voltage change on the skin of your head, you're actually reading something about what electrical signals are going on in the brain. And so it tells you something about how the brain's working. I saw an article yesterday about, a person who has an artificial limb, like arm, that's completely controlled by the brain, right? Doesn't have a little thing to manipulate to say, raise my arm. The person has learned to create different voltages across their head to make it do it. It's pretty awesome. Actually, I said across their head. I didn't read the article carefully. I don't remember where they created it. But that's possible by using things like this because our bodies run on electricity. That's how we communicate. And our muscles run on electricity. You depolarize, repolarize, that's an electrical event. Okay, make sure you know Ohm's law and the directions. You will have a circuit problem on the exam where you're going to have to apply Kirchhoff's laws to solve a circuit. So make sure you know your rules about how many node equations can you make that are unique. How many loop equations can you make that are unique? Make sure you know Kirchhoff's voltage law. The sum of the voltage drops on a loop is zero. What is Kirchhoff's voltage law really based on? Conservation of energy. And make sure you know Kirchhoff's current law, that at any node in the circuit, the amount of current that comes in is equal to the amount of current that leaves, based on conservation of. By the way, it's snowing outside again. Very light. Yeah. Yay. Wait, it doesn't do that in your part of the Philippines? Or any other part? Yeah.
So do you only add the first three nodes, or what is the rule for that?
The rule for the nodes is one less than the total number of essential nodes. Now, since I made that throwaway comment, I'm sure there are places that it snows in the Philippines, right? No? Wow. I used to be all naive and think like, Japan, a little island nation, no snow. Well, they proved me wrong, right? Winter Olympics there. So I have to be a little more careful about those. Oh, it's an island nation. They don't have snow. And some do. And of course, where are the Winter Olympics starting this weekend? In South Korea. Yay. Nothing could possibly go wrong with the Olympics right there next to North Korea when Trump and Kim are, tweeting each other like bunch of mature world leaders. Moving on with our class. One of the cool things that we can now get to is if I have an electric charge, it can have a force on it due to two different things. What are the two different force fields that can put a force on an electric charge? Well, there's the third that we've talked about, but we ignore it. What's the one we ignore? Let's get that out of the way. Gravity. Why do we ignore gravity now? It's pretty important, right? It makes my pen fall and get damaged. Compared to the other ones, the electric and magnetic, it tends to be really weak. You can look at that chart back there where Alex is, and it gives you some numbers about the relative strengths of forces. And gravitational force is by far the weakest. Now, before we completely dismiss gravity, we have to also acknowledge that gravity is the dominant force in cosmology. And you're like, how is a throwaway force? When do we ignore the dominant force? Because electric force can be attractive or repulsive. And as you get more and more material, you're going to have the net charge is just staying pretty close to zero because you're going to be adding a lot of positive and a lot of negative. But with gravity, as you get more and more material, it's all attractive. And so the gravitational charge just grows. And so ultimately, our Earth is held together because of gravitational force, because the electrostatic forces are small because the net charge is not very big compared to the net mass. Likewise for the sun and everything else. Okay, so we ignore the gravitational force unless specifically invoked. You know, if it says what electric field is required to levitate the electron, well, then we're going to use the gravitational field. But if it's not invoked, we're going to ignore gravity. So then what two forces do we pay attention to now? And of course, they're on the screen. Magnetic and electric fields. If I have a stationary charge, only one of those creates a force. Which one creates a force on a stationary charge? Only the electric. But if it's moving, you have both. And so if, because of the direction of the force, the electric force is Q times electric field. The magnetic force is QV cross B. So the forces are proportional to the charge in both cases, but parallel to the electric field and perpendicular to the magnetic field. So one thing that we love to do in physics is to make electric field go one direction and magnetic field go perpendicular to it. And then we have a particle go perpendicular to both of them. So you see in this picture, we have a particle going along the z-axis with the electric field along the x-axis and the magnetic field along the y-axis. Each one of those perpendicular to each other. In that special situation, your electric force, let's assume a positive charge for beginning, your electric force is going to be parallel to the electric field. The magnetic force is going to be perpendicular to the electric field, perpendicular to the magnetic field. And it's going to be perpendicular to the velocity, which means it's either parallel or anti-parallel to the electric field. So you choose your direction of motion to make sure that your magnetic field is the opposite direction of the electric field, and there's only one speed where the two forces will add to zero, where the net force will be zero. And so we can use this as a velocity selector. You'll remember from class last week when I talked about a mass spectrometer. And I said we start with these slow-moving ions, and then we put an electric field, and we accelerate them through like 1,000 volts, so they have a kinetic energy of 1,000 electron volts. And if they start with like 7 volts, we say, well, that plus or minus 7 is small compared to the 100, and we're good. Well, if you're doing precision work, you're not good with that uncertainty. You want to be exact because you're looking for things like, what's the difference in mass between, I of course can't think of any right off the top of my head, but you have lots of combinations where you have two different types of molecules that have the same mass, the same nominal mass, like, I don't know, Yeah, I'm simply not thinking of anything. I swear like CO2 matches with another common thing, but I can't remember, so I'm not going to try to guess it out. But even though they have the same nominal mass, they're not going to have the exact same mass because you have different number of protons and different number of neutrons, and neutrons and protons don't have the same total mass. Very close, but not exactly the same. So you want a high precision instrument that can actually tell the difference between those molecules. So to do that, you use a voltage selector. So you have your source where you're kicking them out at, let's say, 1,000 electron volts of kinetic energy, and then you put them through a cross electric and magnetic field. And based on the strength of the electric field and the magnetic field, you can tune it so there's only one speed that will have a net force of 0. And if they're perpendicular, that calculation is easy. Where do I have it? Okay, I don't have it, so I'll write it out. So we want the net force to be 0, which means that we're going to have that relation. Cancel out those Q's. It just doesn't matter what the charge is now because it was in both terms. And so you have electric field is equal to minus velocity cross magnetic field if electric field is perpendicular to velocity, which is perpendicular to magnetic field. If they're all mutually perpendicular, so I better put another perpendicular. There I've got it covered. They're all mutually perpendicular. Then this is simply electric field magnitude is equal to the speed times the magnetic field. So the only speed that can go straight through with a net force of 0 is electric field divided by magnetic field. And so you specifically choose a speed so you can make this so you have a nominal 1,000 electron volts, and it might have plus or minus 7 electron volts, which normally we consider not a big deal because that's less than 1%. But then you put it through the crossed electric and magnetic fields, and you get out pretty close to exactly 1,000 electron volts, with your plus or minus much, much, much smaller, because anything that was going slower got deviated one way. Anything that was going faster got deviated the other, because the net force is only 0 if you're at the speed you're looking for. And once again, that speed is just, make sure I write that right. Yeah. So there's a very practical use. And now let's get to where this was used in a famous experiment. Look at the time. Oh yeah, we're fine. Famous experiment. Understanding that material had electrons in it. The isolation of the electron occurred completely separately from the understanding that electrons made up part of matter. So where did the understanding that electrons made up part of matter come from? They came from Thomson's cathode ray tube experiments. So what is a cathode ray? Well, we talked about a CRT, a cathode ray tube. That is what a traditional tube television is. So the cathode ray tube has, you see back there where it says cathode. The cathode is on the negative side of the battery, which just confuses me every time I look at it. But what you're doing is you have a little filament that you put current through, and because of that current going through, electrons are boiled off. That's actually the terminology we use. We talk about electrons as if they're a fluid, and when you raise temperature, we say that it boils off electrons. So you have electrons coming off, and the voltage, see it's got a little battery shown right here. You generally don't use a battery. You use an AC source, alternating current, that's about 7 volts AC. And so what you're going to have is electrons coming off with this, well, with an energy that's ranging between plus or minus about 10 volts or 10 electron volts. And then you accelerate them through this big potential difference, so they're going really fast. when they go through the anode, which here is just shown as a plate with a little hole. How does that even work? If I put a negative charge here and a positive charge here, what's that going to do? Okay, electric field lines go out of which and into which? Out of positive into negative. So I'm going to have electric field lines that are going like, and of course they have to come in normal to the surface. So the electric field lines are going to be going like that. They're curved because this isn't two parallel plates. Now, when my charge comes out of that hole, it's a negative charge. It's an electron. So the force on the electron is which direction? It's going to be the opposite direction of the electric field because force is QE. And so the E vector is pointing into the cone because it's a negative charge. The force is out of the cone. And so that's going to make a force that yanks the electron like this. And then you can just do the work-energy relation, something you need to be clear on. The work-energy relation, the work non-conservative is change in kinetic energy plus change in potential energy. In this case, work non-conservative is 0 because we don't have any friction on it. We don't have any machine holding it. So the change in kinetic energy is minus the change in potential energy. But change in potential energy is Q delta V. It's going to a lower potential energy, so the kinetic energy is going up. And you calculate the change in kinetic energy, just boom, right there. The reason we use the electron volt, because you just take the charge in electron charges, multiply by the voltage difference, and you have the kinetic energy in electron volts. So the particles come through that little hole with a very high speed. If your geometry is right, the electrons aren't going to be accelerated to the side, they're just accelerated straight forward through that hole. And so through the hole they go, and then we have the velocity selector. So you only have certain voltage or velocities that come out. Now what Thomson noticed was that the particles were affected by both electric field and magnetic field. And because they were affected by both electric field and magnetic field, he knew they had to be moving charge. And so he went through and determined then that this charge was charge of an electron, and thus there must be electrons back there in that cathode. And from this, he decided that you have to have electrons in matter. And so Thomson came up with a model for matter. We'll talk about this model after the second test, so not after the test coming up. But this model is called the plum pudding model, where he said, okay, we must have material, like the stuff this is made out of, has negative charges, electrons in it. They're kind of like plums or raisins in the plum pudding, and then it just has positive charge kind of spread out everywhere. So he came up with a model for matter saying that you have these little electrons in it, and then you have positive charge spread out everywhere. And that was the model that was being tested in Rutherford's experiment when we get to that. So he determined that we had electrons and material there by using these cross electric and magnetic fields. An application. I don't know how many people here want to be a physician or somebody who works in the medical field, but there are applications of physics, obviously, in any area in life, because physics is awesome. And one of them is a way of measuring the flow rate of blood in a vessel. And you can do that by using an external magnetic field and then measuring the voltage that's produced on opposite sides of a blood vessel. Because if I have charge going through this tube, the blood vessel, and there's a magnetic field, that's going to create a force. It's going to make a force that's QVB if the magnetic field is perpendicular to the flow direction of the blood. Q is the charge of the blood, V is the velocity, B is the direction of the is the magnetic field. And so the charged particles in the blood are going to be either deviated to the top or the bottom depending on if they're positive or negative charges. And they're going to be deviated until you make an electric field that's strong enough to balance the force due to the magnetic field. So you have the blood going through a vessel, you put it in a magnetic field, and it's going to develop an electric field that's perpendicular to the magnetic field that will exactly balance the force of the magnetic field on the blood going through. So using that balanced equation, you right away can say, hey, look, the voltage that I measure, which is going to be approximately V is the voltage difference is approximately electric field times distance, or separation, the diameter of the blood vessel in this case. So electric field is equal to voltage difference you measure over distance. Allows me to determine the speed at which the blood is flowing through. I don't have to cut the vessel and measure how many blood platelets are passing per second. I can use this method to determine the flow rate, how quickly the blood is flowing. It's better, right? Better than cutting a vein or artery. Which leads us to the Hall effect. The Hall effect is basically the same idea. The Hall effect, I have charge flowing through something. I put it in a magnetic field. I measure the voltage necessary to balance the magnetic field's force, and I can determine something about the charge. Now I'm going to skip past this. This is talking about the drift speed of the blood, or not of the blood, but particles. I'm not really concerned about the drift speed. What I am concerned about is what we actually measure with the Hall probe. And to do that, I have to talk about a second equation for magnetic force. So right now we've learned the equation up here for magnetic force. That's the magnetic force on a charge moving in a magnetic field. Force is equal to QV cross V. Wait, what? Okay. So now we're going to move to what happens if I have a bunch of charge flowing, and I would like to talk about the effects of a lot of charge flow instead of just a single charge. Well, this is a lot of complicated stuff, talking about the drift velocity, the density of charge carriers, and the charge of those charge carriers. What I am going to focus on is the outcome of this. I'm not even stopping on this page except for to say it exists. All of that ugliness turns out to be current times length. Now, this page does have one thing that is a technical thing. I am not going to hold you responsible for it, but technically current doesn't have a direction. So we define the length of the path that the current is following as a vector. Because, we have lots of distance vectors. It's kind of arbitrary, I think, but it's a technicality. So, right, this here says current vector equals, and then we say, but we can't define it as a vector, so we make it length. So current times length is this whole crazy thing. So the outcome, this is the important thing from that 2-3 pages, is that if I have a wire carrying current, right, we've been working with current in circuits, the force on the current going through the wire is force is equal to the current in the wire multiplied by the length of the wire crossed with the magnetic field. So now we have two equations that are vitally important for the force on moving charge. QV cross B if you're looking at a point charge, or IL cross B if you're looking at current going through a wire. Now this leads us to lots of new problems we can do. So how would we solve any random problem that has force on a current carrying wire? We'll start with the same rules as we had for a charge moving. That is, if the current is 0, clearly there's no magnetic force due to current. If the wire is parallel to the magnetic field, then that cross product gives us 0 because cross products are multiplying perpendicular components. So if the direction that the current is traveling is parallel to the magnetic field, there's going to be no force. And of course, if the magnetic field is 0, there's no force. Once you've gotten through the conditions that would make it, hey, there's no force, we don't have to worry about it, then find the angle between the length, the path that the charge is or current is going, and the magnetic field. Use the right-hand rule to determine direction, and use the magnitude here, force is equal to ILB, sine of the angle between the current and the direction the current is going, current, the magnetic field, and sine of the angle between the current direction and the magnetic field direction to find the force. So, okay. This one here is written as a problem with variables to solve, but I'm not going to solve it the way that it was written because this here is written to use the drift velocity stuff that I skipped over. But let's talk about how a Hall probe would work based on this picture. So we have a flat slab of semiconductors. So that's what this grayish thing is. It has a thickness of 0.50 millimeters, which is shown there. And it has a width of 1.0 centimeters shown, and a length of 30 centimeters shown. A current of 2 amps is flowing through it. The magnetic field is 0.25 Tesla. And it says, what's the magnitude of the Hall voltage across the slab? So let's start this the easiest way we can. I have a current that is passing as you view it from left to right. The magnetic field, what direction is the magnetic field going in this diagram? The magnetic field. The magnetic field is represented by those X's. What does the X mean? It means it's going away from you, so it's going into the screen. So magnetic field is into the screen. The current is flowing to your right. So what's the direction of the force on the charge carriers? Force equal to IL cross V. So, Michaela, why don't you lead us through this? Oh, wait, I had you do it before, didn't I? Brandon, why don't you lead us through this? We have the right-hand rule for force is equal to IL cross B. I'll write the equation here so you don't forget that. So using our right hand, what do I do first? Okay, the direction of the current, yes. Direction of the current. So I have, which finger is that? Index finger, right. So I start with my index finger going the direction of the current. Then what?
Direction of left versus cross.
The thumb is going to be the direction of the answer. It's going to be the direction of the force. So the middle finger is the direction of the second element. So the middle finger needs to be pointing in the magnetic field direction. So my hand's going to be pointing like this. My thumb is pointing, go ahead and say, up. My thumb is pointing up. So that means that the force on the charge carrier is going to be up. So the force of the charge carrier is up. That means that I'm going to start putting a charge on the top. What will the charge be that goes on the top? Positive or negative? It's a trick question, by the way. Most of us would say, what travels through a wire? Electrons. So we would say if it's an electron, then I'm going to have negative charge. I'm going to have negative charge up there at the top. But this is a semiconductor. And in semiconductors, we find that it goes either way. Sometimes you have electrons traveling through, and sometimes you have what we call holes. What's a hole? A hole is a missing electron. But sometimes the charge carrier can be a hole. In a semiconductor, you can have the charge carrier being a hole. And if the hole is the charge carrier, then there's going to be a force on that missing electron that's upward, and the top would be positive. So one of the first things you can determine with this Hall effect is if it's a positive or a negative charge carrier. So we know that while in wires, it's always negative charge carriers, electrons. In semiconductor, it could be a positive charge carrier, even though that positive charge carrier is actually a missing electron. Okay, so let's say that it's electrons to make life easy. So we have negative charge up here on the top. If I have negative charge up there on the top, what does that make it on the bottom? I'm going to have a net charge of 0, so I put negative on top, what I'm going to be left with on the bottom? Positive. So I'm going to have positive on the bottom. And so that's going to make an electric field. What direction is the electric field in this case? Electric field points out of the positive and into the negative. See, the electric field is pointing like this. So there's my electric field. And then I can make my relationship that the equilibrium is reached when the sum of the force vectors equals 0, which means QE plus QV cross B equals 0. I've carefully selected my directions so they're perpendiculars. And so that's going to come out to the more simple E is equal to VB. Great equation, but that has voltage, or not voltage, speed. I didn't want to use speed. What did I want to use? I measured the current, so I want IL cross B. So my E turns out to be I over QLB. So now I have a relationship that tells me the electric field as a function of what the charge carrier is. Well, in this case, we know the Q is going to have to be the charge of the electron, either positive or negative. The current and the length of the probe and the magnetic field. And so I can determine the magnitude of the voltage by taking, well, the magnitude of the electric field is this. Voltage is equal to electric field times distance, parallel. What distance is parallel to that electric field? We had L, W, and T for the distances. Which one's parallel to the electric field? W. I heard somebody say W. So it's electric field times W is the voltage. So that means the voltage is equal to I can't write.